Right, so for this evening, it's a great privilege to welcome Doug Benn to join us tonight. So, and I think, as you can see from the image on your screen at the moment, we're going to have a spectacular talk on glacial surges, and you can almost, that word surge fits the photograph, I think, incredibly well there. But Doug comes to us today from St Andrews, where he actually started his career working on glaciers a wee while ago, I would say.
Yes,
and he worked on the last glaciers in Scotland, I believe, on Skye.
yes.
But then since then, he's graduated to working on glaciers that are still around, and he worked in many places around the world, Norway, Iceland, North and South America, the Himalayas, and then spent quite some time. He was planning to go to Spitsbergen or Svalbard for a wee while to be working on the department up there at the University of Svalbard, is it called?
University Centre in Svalbard.
University Centre in Svalbard. And he stayed there 10 years. So I think if you've got an interest in glaciers, what better place to be based studying them than Svalbard? But his career's now come back full circle to St Andrews, where he is today as a professor of glaciology, is it, at the University of St Andrews. And I think with his background and experience, we're in for a real treat tonight to have this talk on the glacial surges, which I'll hand you over to Doug now for the talk. Thanks very much.
Great, thank you very much. No, that was a really nice introduction, actually mentioning the earliest work that I did, which was on the last glaciers on the island of Skye, because in this talk, this basically traces a loop up to Svalbard and back to where the journey started on Skye and to see the place for the first time. Okay, so this drawing here at the top, I produced during my postdoc when I was working on the glaciers of Skye, which is a reconstruction of the ice cap and independent glaciers as they were during the Younger Dryas, conventionally dated to 12,900 to 11,700 years ago. And over the years, there's been a lot of work on these glaciers, reconstructing them, reconstructing what they imply for past climates, and so on. And most of these studies have assumed that these glaciers had a steady state relationship with the climate of the time. So that their geometry was in steady state at their maximum, and therefore we can use that geometry to infer equilibrium line altitudes and paleoclimatic implications of that. But one of the questions I'll be asking in this talk is, did glacier surges complicate glacier climate relationships during the Younger Dryas in Scotland? And so in this talk, what I'm going to do is start out talking about surging glaciers and their climatic and geometric controls, and outline a theory of surges, which I've worked on a few years ago now. And then we'll look back to Scotland and look at paleoclimate glacier geometry and evidence for surging in Scotland. And it's really no spoiler to say that by the end of this, I will argue that actually surging glaciers were very widespread in Scotland during the Younger Dryas, including on the island of Skye. So surge type glaciers then. These glaciers have quite distinctive dynamic behavior in that rather than flowing along at a steady rate, they oscillate between slow and fast flow modes on timescales.
How do you is it F1 or F2 that's the thing that
this graph at the top, the red line there shows a velocity record from this glacier here, Morrisoneth Brain. And up until the middle of 2016, it was quite slow moving, around about a meter per day, yeah. But then, quite suddenly, in late 2016, the glacier accelerated and hit a maximum speed of about 15 meters per day. And over the ensuing years, slowed down again with these blips in the summertime when it speeded up again. So really dramatic change in the speed. And prior to the surge, this is a smooth, barely moving glacier. I rode a snowmobile up and down there across the smooth snows. And there, after the surge onset, or the onset of the fast phase of the surge, in 2016, it's a maze of crevasses and impossible to travel across. Now, this speed up here of the glacier, it's not related to any external signal. It's not like something happened just before mid-2016 that made the glacier do that. It's the result of internal changes in the glacier that cause it to switch its dynamics from a slow to a fast state. Now, only about 1% of the world's glaciers are surge type. And so for a long time, they were regarded as anomalous things, as something strange that a minority of glaciers did. But the distribution of surge type glaciers is non-random. There are clusters of them. There's certain regions of the world where there's lots and lots of them. And Svalbard is one of those places. So to give you an idea about what happens in a surge and also part of my personal story, I arrived in Svalbard to take up a position in geology in the beginning of 2006. And this glacier here in 2005 had just done this. And I was part of the group that recovered the cameras from this site. So I was there while this was going on the year before I went to take up the position. And so there you can see that glacier is galloping along at tens of meters per day as the months are ticking through here. So it began just within the picture on the right, and now it's beginning to disappear off the picture to the left. And in August, now we can see this amazing thrusting going on as huge chunks of the permafrost are being ripped up by the glacier and incorporated within this mass of dirty ice. Now, the postgraduate that set up the camera turned it in mid-August to turn around to get the front of the glacier again, and we can see it advancing into the fjord. The front of the glacier is crumbling away by calving, but you can see that the ice itself is still moving forward very, very rapidly indeed. So we're now getting into the autumn. The snow has come back. The days are beginning to get shorter. And very, very soon, we'll see the dark season beginning to come. The very last of the sun, the last day when the sun rises is round about now, towards the end of October. And now we're sliding into the blue season, the beginning of the dark season in Svalbard, and very, very quickly we'll lose the light. And then when the lights come back on again, the glacier is stopped. Now, the position of the glacier when the light came back is not very far. It's only a short distance beyond where it was when the lights went out. So it waited until it had a bit of privacy before it actually terminated. So we didn't actually capture that. But now you can see this transformation. Here's this glacier that had been galloping along at tens of meters per day, and now it is just stopped in its tracks. And that surge, as spectacular as it was, is not the only one. And through, if I can, want to start this animation and I can't get the bar on this. Maybe if I leave that. Yeah. That's a shame. This is a very nice animation, but it's, let me just. I don't want to stop share. I just want to escape the presentation so that I can start this animation. Any help? Yeah, no, I don't think I set this one to just automatically start. I think it needs a click, but then I need to be able to see the arrow, which should be at the bottom of the image.
Okay, so what we're doing is we're just
There it is. There it is. Hit that. Right. There we go. Right. So this is an animation of glacier velocities from satellite. And the color bar there going from blue, very slow, yellow, fastish, red, getting faster, and the white, the purple and white colors are pretty rapidly moving. And you can see that glaciers all over the archipelago are switching on and off in terms of their flow dynamics. It's absolutely remarkable what the glacier dynamics is like on Svalbard. In many regions in the European Alps, for example, glaciers are flowing along at a nice steady pace year upon year, speeding up a bit in the summer, slowing down in the winter. But more or less a steady kind of speed. Here in Svalbard, it's just a free-for-all. These glaciers are switching on, and these are glaciers who may have been inactive for 80 years, 100 years, and then suddenly they wake up and spend 2, 3, 4 years in a very, very rapid state of motion. So when I went to Svalbard, obviously this is something very interesting that was going on, and clearly I was drawn to this as a research topic. And at that time, there was no coherent theory of why surges occurred, why they should cluster in particular areas. And so I made the decision to focus research on surging glaciers and began by doing a global survey, began with a global survey of where surges happen and looking at the possible controls of this. And this is my former PhD student, Heidi Silvestre, absolute powerhouse of a student who really threw herself into the task of understanding glacier surges. And what Heidi found confirmed my hunch, which was that surging glaciers occupy very distinct climatic envelopes. That Heidi basically compiled the first global database of glacier surges, and she also used era 40 reanalysis data to characterize the climate where surging glaciers occurred. And in this plot here, this plots climatic space, mean annual precipitation on the horizontal axis, mean annual temperature on the vertical axis. The gray bubbles are non-surging glaciers, with the size of the bubble representing the number of glaciers in that particular cell. And the magenta circles are the surge-type glaciers. And we can see that there is this distinct cluster in the middle here where the majority of surge-type glaciers occur. There are very, very few of them in Arctic Canada, but in places like Svalbard, Iceland, East Greenland, West Greenland, Alaska, Yukon, high mountain Asia, there are terrific clusters of these things. One of the really striking things about this is the distribution of surge-type glaciers in the Arctic, and this is what we call the Arctic Ring. in which the various surge clusters are indicated by the letters here: Alaska, Yukon, West Greenland, East Greenland, Iceland, Svalbard, Novaya Zemlya. And this region here is delineated by a precipitation contour at 200 millimeters per year, so more than 200 millimeters per year precipitation, and colder than 10 degrees summer temperature. Now that's the era 40 temperature, which is not the temperature at the glacier midline. It's characterizing the mean temperature in that cell. But this, regardless of the precise values, this clearly shows that there's this ring of surge-type glaciers around the subarctic and in Alaska, Yukon. In terms of glacier geometry, there are also regularities there, so that it tends to be the larger glaciers that are surging rather than the smaller ones. So in Iceland, we can see that glaciers over about 8 kilometers in length are much more likely to be surge type than the small glaciers. In Svalbard, similar kind of picture with surges concentrated at the large, low angle end of the distribution. This is percentage of surge type glaciers at different sizes. And we can see that in all of these regions, it's the bigger glaciers that are more likely to surge. So what does it all mean? The framework I developed in order to think about surges was to, first of all, ask the question, why do most glaciers not surge? What is it the glaciers have to do in order to flow along at a constant speed? And in order for that to happen, we need to have an equality between the ice flux, the actual rate that the glacier flows at, and the balance flux. And the balance flux is how fast the glacier ought to be going in order to discharge the snow that falls in the upper part of the glacier and replace the ice that's being lost on the lower part of the glacier. So the glacier is being fed at its upper end by snow, it's losing mass by melting at the lower end, and ice flow is connecting the regions of gains and losses. And so for normal glaciers, what we might call normal glaciers, they're going to plot on this line or close to this line so that the observed ice flux is close to the balance flux. Surge-type glaciers, however, jump from one to the other. They go from a state where the actual ice flux is much less than the balance flux, and ice therefore builds up within the catchment. Then they go into surge, and they're flowing much faster than the balance flux, and they take away ice far quicker than it's being replaced. And then the surge ends, they jump back to this state here. That's on which one? Ah, and then which one? Not draw. That one. No. Yeah. Okay. Yeah. So our surge type glaciers are bouncing between these conditions here, between faster than balanced flux and sorry, the ice flux higher than the balanced flux and then back again. So what is it that has to happen for this equality to be satisfied? Well, basically, the glacier has to be able to find an actual flow speed that matches the balanced flux. No, I can't change slides. Oh dear. Right. We're in business again. Right. Okay. Yeah. Yeah.
You've gone wrong with your pointer again.
Yes. Lost it again.
We'll get there eventually.
Okay. Right. Hopefully we're in business now. Okay. So the actual flux of the glacier is controlled by the driving forces, the weight of the glacier directed down valley, and the resisting stresses, the balance between these forces. And the resisting stresses, the resistance to glacier motion, are basically dependent on ice temperature and water storage. How warm the ice is, how close it is to the melting point, how much water there is at the bed. And collectively, these two things are manifestations of the enthalpy content or energy content of the ice. So this then, once we get that framework in place, we can start to think about how all this is going to play out. The mass balance and geometry determines the balance flux, enthalpy, ice temperature and water, and geometry determines the actual flux. And the link between these two things is the ice flow converts potential energy into enthalpy. Basically, that as the glacier slides over its bed, working against friction, that creates heat. And the potential energy of the glacier is turned into heat at the bed of the glacier. So all these things have got a balance. For a stable, steady state, the flow rate has to match the balance flux. Enthalpy gains, anything that makes the bed wetter or warmer, has to match losses. You've got to get rid of that extra energy, or the glacier is going to speed up. And so a glacier has got to satisfy all these different processes and find the balance in between them. And if it can't do that, that will lead to unsteady behavior or surge cycles. Right, I promise you this is the only slide with equations. Basically, this is the numerical form of the arm-wavy description I just gave about the controls on surging. And to this, I owe Andrew Fowler and Ian Hewitt, who did the maths. But basically, the structure of the model is as I outlined. And this is, as no doubt some of you'll recognize, it's just a pair of differential equations. And one differential equation describes the evolution of the thickness of the glacier. Is it going to thicken or is it going to thin? It can thicken or thin in response to the surface mass balance, accumulation of snow or melting, and the ice flux, how fast ice flows out of our accumulation area on the glacier. This equation here describes the evolution of enthalpy, the energy at the glacier bed. Frictional heating, geothermal heating, conduction of heat away from the bed of the glacier to the ice surface. And this is the water balance, discharge of water away from the glacier along the bed, and inputs of water from the surface. Now, the wonderful thing is that if you evolve this pair of differential equations in a numerical model, then the glacier will either find a steady state and have a constant thickness through time and a constant speed through time, or it will oscillate. And those oscillate, the switch between a stable state and a surge state, an oscillatory state, depends on the climate and the glacier geometry. So it's one of those wonderful moments in science, you know, where you kind of come up with an idea, you write a model, very simple equations, and then the behavior you were interested in emerges from that model. It pops out. We didn't tell the model to speed the glacier up and slow it down and speed it up and slow it down. It just did it with the right combination of input values. This basically shows when the model runs with the glacier slowly thickening through time and then thinning in response to the increase in speed, which carries the ice away here. This also describes all the different feedbacks that occur within the surge evolution. There's another animation. I'm not even going to bother to try and make this one work. Yeah, okay, we'll give it a shot. Right. All right. What did you hit?
Press escape.
Oh, right. Okay, there we go. Here we go. This is a surge of Morsnif brain, which happened while I was living and working in Svalbard. And this gave us the opportunity to really study what happened during a surge. We could really observe the evolution of geometry, the ice speed, and so on. And we were able to test the predictions of the model with this glacier. So it was very, very satisfying state of affairs, really, that allowed us to go from observations to theory and back again. Okay, so with that bit of background in place, to say that we understand why surges happen, and this is due to this imbalance between the energy balance at the glacier bed and the speed that the glacier ought to be going to discharge the ice that accumulates. We can now turn to the second part of the talk and address the question of whether the Arctic Ring was located over Scotland during the Younger Dryas. I haven't got my pointer back, but never mind. Right click. Okay. Oh yeah, there it is. Excellent. Yeah. The Arctic Ring here, that in the colder climates of the Younger Dryas, was the Arctic Ring located over Scotland? It's a really tempting idea. Back when I developed the surge theory, which was in 2018, 2019, I spoke to a number of people who still kind of deal with glacier geomorphology and suggested this idea to them and said, you really ought to have a look at that. But nobody took the bait. And then during the pandemic, I was kind of looking for something to do and thought, oh, I'll do that project. And so my pandemic project was surging glaciers in Scotland. And the results are very interesting. I hope you'll agree. This is a map of generally accepted glacier limits at the peak of the Younger Dryas glaciation, with this West Highland Glacier complex here, satellite ice caps in the Northern Highlands, the Grampians, and on several of the islands. Here we go. Here's the West Highland ice field, Skye, where it all began. So to address the question, were there surge-type glaciers, rather than starting with the geomorphology, with the landform record, I began by asking the question of, was the climatic envelope located over Scotland at the time? So you start out looking at the paleoclimate, and then at glacier geometry, and then finally at the geomorphology. So first of all, climate. Now we're rather blessed in Scotland for the Younger Dryas, in that there's a lot of super work reconstructing temperatures from chironomid assemblages. Chironomid is the family of insects to which midges belong. So finally, here is the reason why midges are here on Earth. It's not to torture geologists, it's to provide us with a paleoclimatic proxy. These lines here are basically temperature reconstructions at a variety of sites, with the scales down here. And the period known as the Younger Dryas, the cold interval, is picked out here in green. Up here is the early Holocene, so these are the warm climates of the early Holocene, and the base of it is the escape from the last ice sheet glaciation. But you can see this cold period here marking out the Younger Dryas at these various sites here, and these 4 were used in the study. Now, if you have temperatures, and if you know the elevation of the equilibrium line of a glacier, where the amount of snow accumulation exactly balances the amount of melting, because the melting has to balance the precipitation, there are relationships that allow you to reconstruct precipitation from if you have the temperature data. And this is from the work of Nick Gollidge, which shows the relationship between summer temperature at the snow line or the equilibrium line of the glacier plotted against precipitation, and we have these relationships here, which vary depending on whether it's a summer or winter dominated precipitation. This illustration has gone a bit weird, but just ignore that. Reconstructing glacier equilibrium line altitudes has been a big thrust of research in Scotland over the past several decades. And so there are many fine papers that have published values of glacier equilibrium line altitudes. And these data were available for the islands of Harris, Skye, Mull, Rum, Arran, the Northern Highlands, and ice caps in the Grampians. And combining those with chironomid inferred temperatures and calculated precipitation values, you have everything you need to know to broadly characterize the climate in Scotland during the Younger Dryas. So this here, annual precipitation, mean summer temperature, with error bars on it for different types of climate, precipitation dominantly in winter or summer or evenly distributed throughout the year. And the parallelogram there delineates the climatic envelope for surging determined from modern day observations. And you can see that except in the unlikely event of summer dominated precipitation in Scotland, all of the data for these different ice caps falls within the optimal climatic envelope. Now, the West Highland ice field, paleoclimatic analysis had not been done for that because nobody has yet attempted a full 3D reconstruction of the West Highland ice field. But we can assume that its climates were intermediate between those of the West Coast and those of the Grampians. And since we have both the West Coast and the Grampians in this distribution, we can assume the West Highland ice field fell in somewhere in about here as well. Probably the climate in Torridon was not that different from Skye. The climate at Loch Tay was not that different from what it is in Dromoctor Pass, for example. So on the basis of the paleoclimatic analysis, then, it corroborates the idea that there could have been a surge cluster in Scotland during the Younger Dryas. Yeah, oh, sorry, I forgot to got that one. West Highland climate about there. For glacial length and slope, modern data from the Randolph Glacier Inventory, Loch Lomond Stade values measured from published maps. So these lines here follow glacier center lines. This is for the far north of Scotland, so that we can calculate average gradients and lengths for these glaciers. These are the distributions I showed you earlier for Iceland and for Svalbard. And here is equivalent data for glaciers in Scotland on Mull, Skye, Ben Massif, West Highland ice field with gradient and glacier length shown on here. And the kind of sizes that we have, Mull, Skye glaciers between 8 and 16 kilometers, West Highland glaciers between 16 and 60 kilometers in length. So in terms of the geometry of these glaciers, they also satisfy the criteria that we've established for places like Svalbard. And if we plot up the lengths by category, by length category for the different ice fields, for Rum, Arran, Harrison, Lewis, Skye, and Mull, we can see that the longer glaciers on Skye and Mull seem to be long enough, whereas in the eastern part of the country, Craigmeggy, the Monolea, Drumoctor, Gyke, and the Cairngorms, there are very few long glaciers, and most glaciers are only a couple of kilometers or a few kilometers long. So on geometric grounds, we might expect not to find surge-type glaciers in the Grampians. So having done that, having seen that climatically and geometrically, we might expect a surge cluster in Scotland during the Younger Dryas, we can now revisit the landform record to see if that helps us. And basically, what we're looking for in the landform record is evidence of fast flow, rapid ice advance, crevassed ice, and stagnation following the surge. This produces a variety of characteristic landforms, thrust block moraines, where soft materials have been thrust up in front of the glacier, drumlins and flutings, Cayman kettle topography and eskers, chaotic hummocky moraine recording stagnation of ice, and geometric ridge networks recording the squeeze of till into basal crevasses. This is maps from Svalbard of a glacier called Finster-Walder-Braen, showing the kind of distribution of landforms left behind by its surge. For glaciers that terminate in fjords, there are similar elements, big thrust block moraines. Black is areas of the fjord that were too shallow for the boat to go over. Red is shallow water, green and blue is deeper water. You can see these wonderful streamlined ridges, these transverse ridges, which are retreat moraines, these wonderful geometric ridge networks that are crevasse-fill ridges. So in Scotland, the dominant paradigm for glaciation, for deglaciation after the maximum of the Younger Dryas was active retreat. What we call active retreat, where the glacier advances a little bit, it retreats a bit. It advances again, it retreats some more, pushing up a series of recessional moraines. And then at the very end of the Younger Dryas, when temperature increases very, very rapidly, the last remnants of the glaciers stagnated away. Actually, my early work on Skye and so on was basically developing this paradigm. This is a series of recessional hummocky moraines in Glen Turret, showing what these land systems are like. And in many areas, that still seems to be correct. In many others, however, it's not. So let's look at some examples where that is not the case. The Lomond and Menteith glaciers, the limits of which are shown on here, had previously been identified as possibly surge type, that had been noticed there was something odd about these areas. The work of Peter Thorpe and then Dave Evans and then his students. later had suggested that these might be surge type, but there was a great deal of tentativeness about suggesting that a Loch Lomond glacier might have surged, simply because it seemed like it was a very unusual thing for a glacier to do. But now that we're armed with the climatic data, we can be a lot more liberal about our interpretation of the landform record. So this is the map that was made by Jim Rose from his very detailed mapping on the ground. And the green there is the big moraines at the limit. There's a bunch of moraines here around Drimmen. But actually, there's a distinct lack of recessional moraines around Loch Lomond, that we don't see retreat stages of the Lomond Glacier. There are, however, a lot of drumlins and quite a lot of ice stagnation topography. The recent availability of nice DEMs, the bluish area is the next map DEM. The gray is higher resolution LiDAR data, available for some areas, not others. But look at these amazing flutings. Absolutely beautiful streamlined landforms, fast flow. This is the limit of the eastern limit of the Loch Lomond Glacier. So we can see here there are these big ridges. The outer ridges shown with the dotted red line. Lovely drumlins there. And in here is a big quarry called Drumbeg. It's inactive now, but Dave Evans and I used to go there and record what we could see. What we find is lots of highly deformed sediments. This is till at the top of the section. And this is what we call a glaciotectonite, which are basically bodies of sand that were frozen, must have been frozen at the time, which are enveloped within an anastomosing matrix of finer grained material that are localized, or areas of localized high strain. So all this stuff here has been sheared. And then at greater depth, there is deltaic sediments. We'll just pass over this very quickly. That showed some nice things, but basically what happened in the Loch Lomond area was that deltas were deposited at the margin of the glacier, and those deltas were then thrust by the advancing glacier and then overridden and sheared. And this is all consistent with surges. The proglacial and subglacial glacier tectonics are consistent with a surging process regime. We find these kinds of things associated with surges in Iceland and Svalbard today. The western margin of the Loch Lomond Glacier, this is at Glen Fruin. Here's the outermost ridges there. These are overridden and streamlined deltaic deposits. You can see lineations in there. And then in the inner part of the system, we have eskers, kames, kettles, and so on, ice stagnation topography. The Menteith Glacier, the Lake of Menteith, has been excavated by glacial erosion, and the contents of the basin are deposited in Ridge A. So there's a big thrust moraine belt from the Lake of Menteith, and also some very, very fine thrust moraines going round to Bucklivy and so on. Jumping to the west coast, the Crerran and Etive glaciers, which are near Oban. These ones here, this is the Crerran Glacier, and there's wonderful thrust moraines with glaciotectonized muds put up with at least 2 of these moraine belts. When we get up valley in Glen Crerran, we have lots of ice stagnation topography. kettle holes, cane terraces, and so on. Glen Etive, the maximum of the Etive Glacier was just out of frame, but the main landform at the terminus is a huge delta terrace with kettle holes in it. And as we go up Glen Etive, no recessional moraines, lots and lots of ice stagnation topography. Bathymetric data, possible crevasse fill ridges at the floor of Loch Etive, a nice esker there. Ice must have been stagnant in this region when that esker was deposited. Otherwise, it would have been sheared out of existence. Island of Mull, if we go there, most of the glaciers, the past glaciers in Mull, we have lots of evidence of active retreat, lots of nested moraines. The big exception is the big lobe that descended to the southeast of the Mull ice cap, the Don and Spelv lobe. And at the limits of that, around Loch Don, we have big thrust moraines, again with glaciotectonized muds, marine muds in there. And here at the western limit of that lobe in Loch Spelv, again, marine muds thrust up into these big ridges and not a recessional moraine in sight. Now to Skye, where it all began. Skye was a classic area for the active retreat paradigm from my early work, but some areas closely resemble surging glacier land systems. One of these is the area around Sligachan, with lots of streamlined ridges and drumlins, big thrust moraine belts, and quite extensive ice stagnation topography. The most recent developments on Skye are that good bathymetric data have become available for many of the fjords around the Skye coast. This is a big submarine ridge at the mouth of Loch Sligachan. And so this appears to be a big thrust moraine ridge at the limit of the Sligachan Glacier. Again, we are not seeing much inside of that. Paper just out yesterday, published online, Bradwell and Benn, 2025. This is from Loch Einert on the eastern side of the Skye ice field, with these wonderful big ridges, 3 of them, M1, M2, and M3, and then little recessional moraines inside. Now, this is very similar to what we see in Svalbard fjords, with thrust moraines, flutings, and then small recessional moraines inside. Now, we were talking a little while ago about ice stagnation following the end of a surge. And for a land-based glacier, the glaciers just die in their tracks, and there are no recessional moraines to record sequential retreat. In a fjord, however, at the ice cliff at the front of the glacier in the fjord, that cliff can advance forward in the wintertime just as a result of the force imbalance at the front of the glacier. During the summer, it melts back, calves back. In the wintertime, advances a little bit. So fjord terminating glaciers can deposit recessional moraines of small size, just little annual push ridges, and that's what these appear to be. So here's the retreat moraines in Loch Einert. This is retreat moraines in Svalbard, a series of these minor ridges. And in this case, we can directly relate those to observations of where the glacier was at the time. Final map from Skye. This is some bathymetric data from Loch Scavaig. So here is Corusc in the heart of the Coolin Hills. Red and orange colors again are shallow water. Submarine ridge between Skye and Soy. It just comes on land on Soy and then swings across and hits Skye again just north of Elgol. Big medial moraine ridge here between the Korusk lobe and the Krethach lobe in there. Again, this looks rather suspiciously like the land systems in Svalbard fjords after surges. So if we reconstruct the ice cap on Skye, all of the big outlets, this is Glenvarrigal, this is Sligachan, Loch Einart, Loch Scabig, and Loch Slappen here. All of these have the characteristic signature of surges. And so my now view is that Skye was a hotspot for surging. So to summarize then, the geomorphological evidence is consistent with surge-type glaciers, one of them on Mull, a wee cluster on Skye, and then right round the West Highland ice field from, I would actually put an extra couple of dots here now in Torridon area, as well as Loch Hourn, Loch Nevis, Loch Shiel, Crerran, Etiv, Loch Awe, Gairloch, Lomond, Menteith, and the Teith Glacier, and quite possibly the Trig Glacier here. But I think there was a lot of it. This is probably, I think, an underestimate of the distribution of surges in Scotland at that time. So I conclude then that there was a surge cluster in Scotland during the Younger Dryas, that surge type and non-surge type glaciers coexisted there as they do in many modern environments. And this has implications for how we interpret the evidence for glacier advance and retreat and what that implies for climate. For example, dating shows that the limit of the Loch Lomond Glacier was very late. It was not long before the end of the Younger Dryas. Now, the climatic evidence shows that the coldest part of the stade was somewhere in the middle, not near the end. And so it has been argued that the late advance of the Lomond Glacier was due to increased precipitation. And a story was unpacked about how the movement of the sea ice and moisture coming off the North Atlantic and so on dumped extra snow on the Lomond Glacier and caused it to advance late in the stade. However, all that goes out the window if it's a surge, because the timing of that event can be completely decoupled from the details of the climatic signal. It's a purely dynamic thing. Actually, I think as we begin to get more dates on the timing of glacier advances in Scotland, I think we'll begin to see a lot of asynchrony between the timing of advances in different parts of the country. And taking surges into account, I believe, is a very important thing in terms of understanding landscape evolution and change. Thank you very much.